Hey everybody, welcome back. We are still talking about rational functions and end behavior, but instead of looking at specific values, we're going to be looking at end behavior in a more conceptual way. Okay, so before we would plug in values and see what was happening to them as we increased values either to the left or the right? So if I was looking to see what's going on with this function and I wanted to see what's happening when, let's say, it's a really, really, really big number, like 100 million, okay? So like when x is 100 million, that's 2 times 100 million plus 3 all over 100 million squared minus 4 times 100 million minus 32. So I want you to kind of think about like, okay, if we're talking about 100 millions, if I have 100 million plus 3, does that even really make a big deal? It really doesn't. So in the scheme of the values that we're talking about, it's really not a big deal, okay? Same thing with this 32. If you've got 4 times 100 million and then 100 million squared, again, this really, really doesn't matter, okay? In the context of 2 times 100 million and 100 million squared, think about how many zeros that is going to be. 100 million squared is going to be, 14 zeros minus 4 times 100 million. These in concept really don't matter in comparison to how much there's going to be. So it's like we're comparing 1 to 100 million on the bottom, okay? Or something like some really, really, really big number. If I take $1, let's say, and divide it into 100 million people, how much money do you think they really have? It's not even enough to say it's a cent. It's about 0. So what we're talking about is comparing really, really, really large scaled numbers. And when we're talking about how big these numbers are in comparison, it could be really, really big or really, really small. Like dividing something by 100 million means it's basically 0. So what does this do for us? If I'm looking at this function and I'm plugging in a value like negative 100 million, I'm going to get 1 over negative 100 million, which is essentially 0. And the same thing here, if I'm plugging in x is going to 100 million positively, it's also going to be 1 over 100 million, which is going to be 0. So how can I do that a little bit more directly? So here's what I want you to think about when we're talking about the scale of these really, really, really big numbers. Okay, I want you to think about what are the heaviest hitters as far as the numerator and the denominator. I see that the leading term here in the numerator is 2x and the leading denominator term is x squared. So the hack or the shortcut to this is that you're just going to compare what's the biggest degree in the top and the bottom. So we've got, it's like we're comparing 2x over x squared. As we do that, we can see this x and one of these x's cancels. So I'm left kind of compared to actually one of these x's. Let me replace that with one of these x's. So as I'm plugging in a value, like if I'm going to negative infinity, right? What's 2 over negative infinity? Well, dividing 2 by an infinitely small number is like dividing it to 0. And 2 divided by a really, really, really infinitely big number is also like dividing it to 0 as well. Okay, so for this idea of inputs of a really, really big magnitude, in this case, the polynomial in the denominator here dominated. D-O-M-I-N-A. It dominates the polynomial in the numerator because it's so much bigger. That power means it's going to overcome the overall polynomial. So let's see what that looks like for example 2. So again, in example 2, I really only care about those leading terms. So what I'm really looking at is x to the third over 5x squared, okay? 2 of these x's cancels out with 2 of those, and I'm left with x over 5. So if I'm looking at what this would look like for infinity, that's like saying, okay, if it was positive infinity divided by 5, that's essentially still infinity, right? Or if it was negative infinity by 5, that's essentially still dividing by negative infinity, right? So our end behavior here is the limit as x approaches negative infinity, that's right here. It's still going to be approaching negative infinity, okay? And then our limit as x approaches positive infinity for g of x here is infinity divided by 5, which is still positive infinity forever. Okay, let's look at this next one. Again, we're looking at the biggest term on the top over the biggest term on the bottom. 2t over t. Really, these t's cancel, and I'm just looking at 2. This tells me that we have a constant for our end behavior, that the limit as t approaches negative infinity, h of t is going to equal 2, and the limit as t approaches positive infinity, h of t also approaches 2. This tells me also that there's a horizontal asymptote. With that said, let's talk about how do we find horizontal asymptotes with 3 different cases. Okay, so if the degree of the denominator is bigger, that's when we see something like this. Okay, so if I were to simplify that down, that's like saying 4 over x, which is like saying 4 divided by infinity, which means this is going to be infinitely small and it's going to go to 0. So we have a horizontal asymptote of y equals 0. So when the denominator is bigger, that horizontal asymptote is always at y equals 0. If we're looking at the degree on top being bigger, okay, so if I look here and I look here, I can simplify that to like saying x squared over 4x. That's like dividing x by 4. So an infinitely big number divided by 4 is still pretty big, which means there's no horizontal asymptote because it's going to be going on forever. So there is none here. And then lastly, when the degrees are the same, okay, so x squared over 3x squared, those x squareds are going to cancel, and I'm left with 1/3. This is a constant. So our horizontal asymptote in this case is y equals 1/3. But in general, when the degrees are the same, you're going to say y equals, we'll call that a over b, where a and b are the leading coefficients of the numerator and the denominator. Okay, so again, these are cases where the degrees are the same, the degrees where the numerator is bigger, or the degrees where the denominator is bigger, depending on which case you have. So let's look at this in another way. So here's our standard form of what a rational function would look like if it had a ton of variables. Really what we're talking about here is our numerator function and our denominator function, the only one we care about. We don't care about any of this other stuff. We care about the leading term and the leading term in the numerator and the denominator, okay? So again, if the numerator degree is less than the denominator degree, then the line y equals 0 is a horizontal asymptote. If the numerator degree is bigger than the denominator degree, there's no asymptote. And if the degrees are the same, then we use the leading coefficients as their horizontal asymptote. So let's talk about this one. So if I'm looking at this, because this is in factored form, we're going to need to multiply out the first terms to see what the leading term is. So x times 2x gives me 2x squared. So I'm going to compare that 2x squared to this x squared. I'm looking at this and I notice, hey, these have the same degree. They're going to cancel out and I'm left with 2 over 1 or just 2. So this tells me that the horizontal asymptote is also at 2. And for example, number 5, so again, I'm looking at the degrees. I see this is 3, this is 2. This is where the numerator is bigger than the denominator, right? So if I'm looking at this, if the numerator degree is greater than the denominator degree, then I know here it has no horizontal asymptote. So if I'm looking at that limit, that would be like going to 3x over x, which would be like saying negative infinity. I'm sorry, not over x, just 1x over 1. That'd just be negative infinity. So the limit would go to negative infinity, but there's no horizontal asymptote. All right, let's do some quick practice to find the end behavior. So again, we're just comparing t squared over 4t. So again, the numerator is greater. So I know that there's no horizontal asymptote, but if I look at this, this is really saying t over 4, which if I'm looking at this as the limit approaches negative infinity, What's d of t doing? I'm sorry, this is t. So then I would say, okay, what's negative infinity over 4? Well, that's still negative infinity. And the limit as t, I did it again, approaches in positive infinity, that would be like saying, what's infinity over 4? Well, that's still just positive infinity. Okay, let's look at this one. X to the 4th over 4x to the 5th. So we do know that this does have a horizontal asymptote of y equals 0 if we look at our chart. So as I'm looking from negative infinity, we're going to compare this. This is like saying 1 over 4x, right? If I'm looking at that, 1 over 4 times negative infinity is still like saying 1 over negative infinity. Well, 1 divided by an infinitely negative number, that's going to be like saying 0. So we say g of x is going to 0. And the limit as x approaches positive infinity, again, would be 1 over positive infinity, which would also be 0, which agrees with our y equals 0 horizontal asymptote based on our chart. And lastly, if I'm just looking at the limit as n approaches negative infinity, again, we're comparing here. So this is like saying 3n to the 5th over n cubed. These are going to cancel. So we end up with 3n squared all over 1. And if I plug in negative infinity here, 3 times negative infinity squared all over 1. Well, negative times itself is a positive, so this would be like saying 3 times positive infinity over 1, which would just be positive infinity. So the limit here would be positive infinity, which means that there's no horizontal asymptote. All right, guys, I'll see you next class.